In this lesson, we'll look at the conversion from component to polar in 3 dimensions. So if we recall from the last lesson, in 3 dimensions, we have 3 direction vectors, so I, j, and k. We have an x, a y, and a z distance. So if we draw that in, here's our x displacement in the I direction, our y displacement in the j direction, and what they do is create the base of our 3-dimensional vector. Okay, and if you recall, we've got this angle here, which we call the azimuth. When we then have a displacement in the k direction, we call that z, and so we get our third component in the k direction, z. So we end up with our 3-dimensional vector. So we end up with 2 right-angle triangles. This is called the altitude. So the 3 components that make up the vector in polar form are the magnitude, is the magnitude here of our vector A, so essentially the length. We've got our azimuth, so that's that base angle, and then we've got our altitude, which is the angle that expands that vector into 3 dimensions. So if we recall, in component form, we have a vector that is A is equal to xi plus y j plus zk. And in polar form, we have a vector which is simply A is equal to the magnitude, the azimuth, and the altitude. Okay, so the conversion from component to polar is relatively straightforward. Obviously, we start off by calculating the magnitude, and the magnitude just utilizes 3-dimensional Pythagoras. So essentially, we're saying that the magnitude squared is equal to the x distance squared plus the y distance squared and the z distance squared. So therefore our magnitude will be equal to the square root of the sum of the squares of all those component displacements. So that's it. That's how we calculate the magnitude. The azimuth is also very simple because you can see that the components that are important in the azimuth is the x and the y displacements. So to calculate that azimuth, essentially we're just looking at the arctan, because it's opposite over adjacent, the arctan of y on x. So it's as simple as that. The azimuth is equal to arctan of the y displacement on the x displacement. Now finally, when we look at the altitude, the important components in the altitude are going to be the magnitude and our z displacement, so that vertical displacement. So in order to calculate that now, we're looking at the opposite and the hypotenuse. So it means we're looking at arcsine. So the altitude is as simple as going, the altitude is arcsine of z on the magnitude. So obviously we need the magnitude to be able to calculate that. And we end up with 3 really simple calculations to complete the conversion from component to polar. Okay, so skill-wise, this is relatively simple. Now, probably the most important thing to remember when we're performing these conversions is that each of these has a domain. Now, obviously, with the magnitude, it's relatively straightforward in that that magnitude will just be an element of a set of positive real numbers. In other words, it will be greater than 0. And it can be rational or irrational, but it must be real. We cannot have negative magnitudes. The azimuth will be much like our 2-dimensional conversion, so that azimuth will be an element of a set between negative 360 degrees and 360 degrees. Obviously, there's coterminal options there, but we can use the negative and positive directions when determining the angle. Positive angle will be in this direction, negative angle will be in that direction. And again, we start at 0 degrees from that positive x-axis. Altitude can only be between negative 90 degrees and 90 degrees. So that is, when we're talking about that altitude, then we can have positive and negative direction, but it's essentially an angle of elevation or depression that we're talking about. So angle up, angle down. We just have to be really careful when we're calculating the azimuth and the altitude to make sure that we get it in the right quadrant, so we're not making silly errors. All right, we'll look at a couple of examples. So in this simple example, we're looking to convert the vector A, which is 1 in the I direction, 2 in the J direction, and negative √3 in the K direction to polar form. So it doesn't hurt to sketch this out first. So rough sketch is fine. It gives us an idea of where everything sits. So we're going 1 in the I direction, so there's 1. Going 2 in the J direction, so there's 2 there. So there's our base. And we're going down, so we're going negative √3 in that K direction, which means that we've got a vector with an angle of depression. So essentially it's important to understand that while that azimuth will be easy to calculate because it's just in the first quadrant, the altitude will have to be negative. Okay, so we'll start with the magnitude. Magnitude is equal to the square root of the sum of the component squares. So we're going to have square root of 1 squared plus 2 squared plus √3 squared. Means we're looking at square root of 5 plus 3, which is square root of 8. So we end up with 2√2 as our magnitude. Our azimuth is just arctan of y on x, which means we're looking at arctan of 2 on 1. So arctan of 2 will approximately be 63.4 degrees. And our altitude will be arcsine of z on the magnitude. So we end up with arcsine of √3 on 2√2 or √8, depending on what you want to do. Now it's important to realize again, because this is going down, this is going to be negative, so it's negative arcsine, and so that ends up being negative 37.8 degrees approximately, which means our vector A is 2√2, 63.4 degrees, and negative 37.8 degrees. Right, so our conversion is as simple as that. When we look at a second example, so in this example we're just looking to convert B, which is negative 5i plus 5j and 1 in the K direction to polar form. So if we set this up again and we do a quick sketch, then we're looking at negative 5. So we'll see we won't start in quadrant 1, we're going to start in quadrant 2. So negative 5, 5 in the y direction, which gives us our base, and our azimuth, and then 1 up, which gives us our altitude. So you can see that's hard to draw and difficult to see. In this type of scenario, it's probably easy to break it down into the two right angle triangles. So if I'm looking at the azimuth, I just worry about the x and the y components. So if we just look in 2 dimensions at the x and y components, or the I and j directions, we end up with negative 5 and positive 5, and we've got a vector in quadrant 2. So we've got an acute angle there, and if you're comfortable with your two-dimensional conversions, we should know straight away azimuth is going to be 180 degrees, subtract the acute angle, and the acute angle in this case is going to be arctan of 5 on 5. And that's because it's in that quadrant 2. So we end up with 180 subtract 45, and we get 135 degrees. That's our azimuth. Our magnitude is really simple. Square root of the sum of the squares, so 5 squared plus 5 squared plus 1 squared gives a square root of 51. And our altitude, as the k value is positive, will be positive as well. So it just ends up being positive arcsine of z on the magnitude. So we get arcsine of 1 on square root 51. And so altitude is approximately 8.05 degrees. Or you could probably even go 8 degrees there. So our conversion here, B, is equal to the magnitude, root 51, the azimuth, which is 135 degrees, and the altitude 8 degrees. Okay, That completes the lesson on conversion in 3 dimensions between component and polar.